Hello. In this lesson I'm going to be looking at a few topics here. We're going to be looking at the concept of doing work, and I'll explain what that means in a minute, and then we're going to look at the difference between weight and mass, and then we're going to go outside and do a little experiment about the conservation of kinetic and potential and elastic energy and how energy is transferred from one type to another. Right, so let's get started by talking about doing work. Now, when we say we're doing work, we're actually using some energy. Now, I have got here just things I can find around the house. Got a new tub of Marmite here, and I have a Newton meter which measures how hard I am pulling it. Now, what I'm going to do is I'm going to pull with a force. It takes 1 Newton, it says on here, to move this Marmite here. So I move that 1 meter along the desk, and that has used 1 joule of my energy. So I had quite a big lunch today, so I've just worked some of it off there. I've worked off a joule of energy, but I'm going to have to do that quite a lot before I can lose the weight that I probably need to lose. So if you can move with 1 Newton, a length of 1 meter, you have used 1 joule of energy. And this is what we're talking about with work done up here. So if you do some work, you can work out how much energy you've actually used if you know how much force you've used and how far you have moved it. Now in the future you'll realize you need to learn about 20 different equations for your physics GCSEs, and there's some rhymes for all of these, and as the time goes on you'll discover something called the Funku rap, which is full of these things. But for now, what I tell my classes is how to remember this is, if you're doing work, you're using joules. That's force times distance, you crazy fools. It sounds a bit stupid, but you say it a few times and you remember it. So we have got a way of measuring up how much energy we have used by knowing how hard we're pulling something and how far we've pulled it, and so there we can work out how much energy we've used. So if I had my my jar of Marmite again, and this has got a mass of 800 grams. It says 500 grams of Marmite, but there's 300 grams of glass and plastic in there as well. So what if I was to move that up in the air a little bit? Let's say I was to take my Marmite and lift it up by 50 centimeters. There we go. So I have moved ½ meter. So I have moved, let's have a look over here. My work done, I'm going to abbreviate it to WD, is the force, which I call F, times by the distance. Now the distance I've moved was ½ meter, so if that's 0.5, what is the force that I've used? Now we don't know the force because we only know the mass, which is in grams, and if I was on the moon it would be much easier to lift this up. I wouldn't need to use anywhere near the amount of force. So we talk about something called weight, and the weight is how the mass of something is pulled down by the force of gravity from wherever you are. So if I went to the moon, my weight would be much less, but that wouldn't mean that I'd slim down at all. It just means that the force of gravity would be pulling down much less on my mass. So what we do with mass, I've got this second equation up here, is your weight is a force in newtons of how hard you're being pulled down by the force of gravity wherever you happen to be. Now for most of us it's usually on the earth. So the force of gravity on the earth pulls down with 9.8 newtons, more or less 10 newtons for every kilogram of mass that there is. So this thing here has a mass of 800 grams, which is 0.8. Let's put that a little bit higher. So we've got the weight is 0.8 kilograms times by gravity, and I'm going to say gravity is 10 newtons for every kilogram. So the weight of this is 0.8 kilograms being pulled down with 10 newtons for every kilogram that there is. So that works out at a force of 8 newtons, and that is the weight of this thing being pulled down. So now in here with my force, I can say I've been pulled down with a force of 8 newtons, or I've had to overcome that by using 8 newtons to lift this up. I've lifted it ½ meter, and so there, 8 times a half, I have used 4 joules of energy. So 4 times as much energy as I did when I pulled it across the table. So I'll do that a few more reps of that and I'll work my lunch off. So that's doing your work, which is how much joules of energy you use while you're doing something. And then we've looked at your weight, and there's a rhyme for weight as well, because when you weigh yourself, you're measuring the force in joules. So we say mass times gravity makes your weight in newtons. Get your units straight. Right, now for the next bit of the lesson, I want to go outside and do an experiment, and we are going to look at how energy is transformed from one type to another. So let me just clear this board and we can see what we got here. This is like being in a proper lesson all of a sudden. So out in the garden, I have got a catapult which I have made. Let's move this down here a little bit. So we're going to pull that thing down, and I'm going to let go of a tennis ball which is going to fly up into the air, and it's going to fly up into the air to a point here, get as high as it's going to go, and then it's going to fall down to the ground again. So when I am pulled this catapult down, before I've let go, it has got elastic energy in it. So let's say that has got elastic energy stored in it. We spoke about energy stores. As I let go of that, the elastic energy is going to make the tennis ball move up. So then it's going to have kinetic energy, which is the movement energy which we spoke about. And then right at the very top of its arc up here, it's not going to be moving at all. It's gone as high as it can. It's just going to stop just before it falls down again. But all that kinetic energy is not lost. Remember, it's just changed from one type of energy to another. And so at the top here, we have got gravitational energy. I'm going to call it gravitational potential energy, and that is its maximum. That's as high as it's going to get. And here the kinetic energy is 0, because all of that kinetic energy, it's actually stopped moving once it gets up there. And then when it starts falling down again, just before it hits the ground here, its kinetic energy here, it's going as fast as it can. So it's the maximum it's ever going to go just before it hits the ground. And because it's virtually at the floor, it's lost all of that gravitational energy. So all the gravitational energy that was there is now been turned into kinetic energy here. So here the kinetic energy is the maximum, and the gravitational potential energy is 0. It's lost all of that stuff that it had. So we started off here with elastic energy. And then we turned that into kinetic energy as it's going up here. And then the kinetic energy at the top has all been turned into gravitational potential energy. And then as it falls down, all that gravitational potential energy is turned into kinetic energy. And then when it hits the ground, it makes a thud. And so that will be some sound energy coming off of there. And there is also going to be some thermal energy. So, like we said, we don't make energy, we don't destroy energy, we just change it from one type of energy to another. So I'm going to put some elastic energy in to hold it in the spring that I'm going to let go, and then that will make it move. It will turn into kinetic energy. It stops at the top, turned into all the kinetic energy is turned into gravitational energy, and then all of that gravitational energy is turned into kinetic energy, which is at its maximum just before it hits the ground. Right, so should we go and see what that looks like as an experiment? I'm going to be assisted in this instant by my son Harry, and also by Peggy the Wonder Dog, who's come out to help because it involves tennis balls. So let's have a look. So this is a catapult with a couple of bungees on it, and a little cradle that can hold a tennis ball which we can fire up into the air. The scale here shows how far down we've pulled the catapults. This is the extension, and we're going to see how much we need to pull it down to make it as high as the house. Okay, Harry?
Way too high.
Down to about 27.
Perfect.
Right, so we found there, with a little bit of help from Peggy, that an extension of 27 centimetres reached the height of the house. Now we've already... Right, that was fun. So you will have seen out there using the catapult, as I said, we fired a tennis ball up into the air, and I found out that if I had an extension of 27 centimeters, then I got the tennis ball roughly to the top of the back wall of the house. Now the back wall of the house was 3.5 meters above where I set the tennis ball off from, and I measured that through a bit of similar triangles and a bit of maths, which I shall put up just as a slide at the end if you want to stay and see if you can work out how that happened. So anyway, the ball went up 3.5 meters. And from that we can work out the gravity energy, because obviously the more mass or the heavier something is and the higher it is, the more gravity energy it has, because it can fall harder to the ground. So next thing we need to know is we need to know an equation for gravity energy. Now if I just back off over here, remember we did the weight is the mass times the gravity. Mass times gravity makes your weight in newtons, get your units straight. And then gravity energy, if you know the weight, which is mass times gravity, and you know how high it went up in the air, then you can work out how much gravitational energy it has just by being up that high and being that heavy. So we can say gravity energy can be found, just multiply the weight by the height above ground. Now the weight is mass times by the gravity. So over here on this board, I'm using abbreviations because I haven't got a lot of space. I've put GPE is a gravitational potential energy. It's the weight, which I've called W, and G, which is the force of gravity on this planet. But instead of W, we know that the weight is the mass times by the gravity. I've made a mistake here. Look at this. I'm not even going to edit my things. It's the weight multiplied by the height above ground. Makes it more realistic. So the weight times by the height, the weight is the mass times by the gravity times by the height. So the gravitational potential energy is mass times gravity times height. Now the tennis ball, I put that on the kitchen scales and I got a mass of 620 grams, but remember you've got to get the units in the right place. So 620 grams is a mass of 0.62 kilograms, which is what we should be using. Gravity, in this instance, I'm going to say it's 10 newtons for every kilogram. And then the height above ground was 3.5 meters. And if you multiply all of those together, 0.62 times by 10 times by 3.5, you get 21 joules of energy. Once that tennis ball was 3.5 meters up off the ground. So we have got that. So this gravitational potential energy at the top here is 21.0 joules. Let's have 0.0 so we know that we're working to the right number of significant figures. So how can we use that to calculate how fast the ball was falling? Now you remember that at the top you had the maximum gravitational potential energy, but by the time it got down to the bottom here, gravitational potential energy is all gone. But it's not gone, because we don't lose energy, we just change it from one form into another. So by the time it got to the floor, or this instant before it got to the floor, it is going as fast as it was ever going to go. And so all of that gravitational energy is turned into kinetic energy. Now I'm going to say kinetic energy as KE, because I haven't got a lot of space, and we know that the kinetic energy just before it hit the ground was 21.0 joules. Now, do we have an equation for kinetic energy? Well, yes, we do, which is over here, and it says kinetic energy. For this, you need to know the mass of it, and you need to know how fast it was going. We're talking about velocity at the moment. If you're not sure about the difference between velocity and speed, I suggest you get onto YouTube and you Google speed, velocity, and a band called They Might Be Giants, and there's a lovely song, and you only have to see it once and you will know the difference between speed and velocity for the rest of your lives. So the kinetic energy is half of the mass times by the velocity squared. So whatever number you get for the velocity, you times it by itself. So kinetic energy is half of the mass, which is m, multiplied by the velocity squared. So I'm going to put that up here, half of the mass multiplied by the velocity squared. Now velocity squared is velocity times velocity, so as many of my old students will tell you, kinetic energy will move me with a half an m and a v times v. So half of m and then v squared is v times v. So whittering away here, what have we got? We got 2.10 joules is the same as half of the mass times by the velocity squared. But we know some of this. We know the mass. We know that the mass is 0.62. So half of the mass is 0.31 times by the velocity squared. Are we getting anywhere? Now, hopefully you can rearrange some equations. And what we've got here, we have got 21.0 is 0.3 times the velocity squared. Now, because this is 0.31 is a multiplied number, the opposite of multiplying is divide. So if we move it to the other side of the equation, we put 21.0 divided by 0.31 equals the velocity squared. Is that going to help us? Can we work out what that is? 21 divided by 0.31. Let's have a look on here. And we get an answer of, it looks about right, 67.7. Someone's trying to get hold of me. 67.7. So then what can we do with that? We know that v squared is 67.7, so we can do a square root. We can find out which two numbers multiplied together gives you 67.7, and on your calculator you will have a square root. I've got one here on my phone which keeps going off. So we have got 67.7, and the square root of that gives me an answer of 67.7 square root of that gives me an answer of 8.2 meters per second. And you get questions like this all the time in the exams. If you know the gravitational potential energy, it asks you how fast it was going when it hits the ground, and all you need to know is that the gravitational potential energy at the top is the same as the kinetic energy at the bottom, and then you do some calculations. Okay, right, just turned off notifications on my phone so we can try this again properly. So where did we get to? We found out that the ball was travelling at 8.2 meters per second just before it hit the ground, and we found that out from the gravitational potential energy. What else could we find out? Now, down here, it says that the elastic potential energy, the potential energy stored in the elastic as you were pulling it down before you let it go, depends on the extension, how far you pulled it down in meters, and by something called the spring constant, because not all springs and elastics and bungees are as stretchy as each other. Some of them need more force to stretch them by the certain amount. So the spring constant is how many newtons you need to stretch something or to squash something by 1 meter. So we could now see if we can work out what the spring constant of the bungees were, because the elastic potential energy that you had at the start was all turned into this gravitational potential energy at the top. So, and if that was 21 joules, we know that the elastic potential energy was also 21 joules because it's just been turned from one type of thing into another. So let's have a look over here. I am going to say, I'm going to call it EPE, the elastic potential energy, is half of something called K, which is the stretchiness of the spring, multiplied by the extension squared. Now the elastic potential energy, we know what that is, because it's the same as everything here. It is 21, and that is the same as half of this mysterious number called K multiplied by the extension squared. Now I pulled the catapult down by 27 centimeters. You all remember from the video outside. So 27 centimeters, remember we don't use centimeters, we use meters, so that's 0.27 squared. So now let's see if we can do some maths here. So 21 is a half of 0.27 squared, and I'd written that down here, which is 0.073 times by k, and you'll see I've put k at the end of this sum here because if you multiply things together it doesn't matter which order they come in. 3 times 6 is the same as 6 times 3, so you can move things backwards and forwards as long as they're all being multiplied. So we have now got half of 0.073 multiplied by k gives you 21, which is 0.0365 times k gives you 21, and then again we can move this across to the other side of the equation because it's a multiplying. We can do a dividing, so we do 21 divided by 0.0365 gives me an answer of 575 newtons per meter. So if I wanted to pull that bungee down by 1 meter, I did a quarter of a meter, did about 27 centimeters. If I wanted to pull that down a full meter, I would have to put in 575 newtons of force, and if I kept doing that over and over, I might eventually then work off my lunch. So I think that is just about it for this lesson. As ever, all of this stuff has come from the AQA physics book, and we have been looking at topics P1 or 1.3 all the way through to P1.5. So if you want to look through that, and then there's questions to do at the end of that as well. And that's it for today. See you next time.